somehow there is a stagnated region. Okay, somehow there's a stagnated region. So we are going to use Mohs circle. Okay, we're going to apply what we learned on Mohs circle to explain why. Okay, there is this stagnated zone. So I'm going to draw that now. Okay. Okay, so we're going to draw. Okay, we're going to draw the feature to explain why there's a stagnated region, okay, where the material is not moving at all. Okay, and again, all we need to do is to apply Mohs circle, which I taught you for the last 2 weeks for designing a carbon fiber. Okay, we're going to apply the same Mohs circle. Right. So let's look at the tool now. Okay, so I'm now drawing the tool now. Okay. Okay, so the I don't think I need some. Okay. So over here, this is the tool. All right. And this is about 1/3 the radius. Okay. So I'm going to sketch for you or for us, okay, the velocity profile. But before I go that, I will call this the rake face. So you know what we are looking at. So I'll call this our clearance phase. Okay. So I'm going to sketch the velocity profile. Okay. So the velocity profile, right, there is distance, and the velocity profile is such that at the interface, right? So this is where our chip is. Okay, I'm writing on the chip side. Okay, so we have a velocity profile doing this. Okay. So the longer the arrow means the faster velocity. Okay, so this is VC, right? The longest one is VC. That is our chip velocity. So that's the distribution of the profile. Then on the clearance phase, okay, at this region we can also sketch a velocity profile. Okay, so the velocity profile is the same thing. Only now, furthest away is the U, which is our cutting speed. Okay, so the shorter the arrow, the lower the speed. Right? Okay. So what we are trying to do is to prove the the present of the stagnated region. Okay. So when there's a stagnated region, means velocity is relatively equal to 0. Okay. So now, if we have an element here, all right, if we have an element here, and if we have an element here, right? Now the question is, right? So we have element 1, we have element 2, right? You have element 1, we have element 2. So if you see how the element 1 will deform, okay, we look at how the element 1 will deform, because further away from the interface, okay, so this surface is what we call our 2 chip interface. And over here is what we call our workpiece or 2 workpiece. Okay, interface. So further away from the interface, right, the velocity is quicker than at the interface. That's what this diagram is showing us. Okay, so at the interface, the velocity is slow. Further away is very fast. So how the element will distort is it will deform this way. Okay, it will deform that way. And then how element 2 will deform, it will deform this way. Okay, so let me write element 2 in the right orientation. Okay, element 1, sorry. So element 1, if I'm going to write in the right orientation, this is known as element, hey, come on, Eugene, it's just a E. Element, okay, hey, element 1, okay, that is element. So if you look at how the element deform, okay, we're going to look at how the element deform. So element 1, okay, element 1 will deform this way. Okay, so I'm going to draw element 1. Okay, so element 1, and then we're going to draw element 2. All right, so if we see how element 1 deform this way, and then element 2 deform this way, right? Can anyone tell me element 1, is it positive or negative shear? Anyone? Cannot remember? So if you look at positive shear,
element 1 would be negative.
Well done. Okay, so let me recall. Okay, let me help me recall. Let me get rid of this diagram. Well done. So if I were to draw positive shear, all right, so this is our element, all right, and because positive shear, the configuration is like this, right? So if I draw the deformation, this is for positive shear, okay? And then if I'm going to sketch negative shear, negative shear, right? So the element, the shearing stress will look this way, right? So this is what we call negative shear, right? You can see that. So if you look at element 1 is negative shear, right? Element 2, right? Element 1 is negative shear because you look at this region and here is the same. Element 2 is positive shear. Okay, so if you look at this region over here and this region over here is exactly the same. Okay, so there's positive and negative shear for you. Okay, well done. So now, if we're going to draw, if we're going to label a point now down here. So if I'm going to label a point A, right? At this point down here is my point B, right? And at a certain point down here, this is my point C. Okay, so what we're going to do now is we're going to draw how the shear stress is distributed. Okay, how the shear stress is distributed. So I'm going to get rid of this over here. Okay, so we are going to view how the shear stress distribution look like. Okay, so I'm going to have two axes. Okay, so this is shear stress. Okay, and the horizontal axis. Right, the horizontal axis is our distance. Okay, then over here This is my point A. At the center is my point B. And then a certain distance, this is my point C. Okay. So from A to B, we know it's negative shear, right? Or close to B. And B to C, right, is positive shear. So over here, I put shear positive. Over here, this is shear negative, right? So now, from negative to positive, because this is a continuous material, right, it has to go to point B. Right? So this is how the shear stress distribution look like, right? You one side you have positive shear, the other side you have negative shear. So at point B, right? At point B, when the shear stress is equal to 0, right? Shear stress is equal to 0 means the material is not shear, moving in shear, but it's holding down enormous stress. Okay, so i.e. the velocity is equal to 0. Okay, so when the velocity is 0 means velocity in both components, x and y transformation. So I'm going to draw a transformation down here. Okay, so if this is x and this is y, okay, so if the velocity is 0 in both x and y, okay, this is what we call our stagnated zone. So the material is stuck down there and it's not moving at all. Okay, and we saw that, right? We saw that in our on the YouTube video. Yes or no? You guys saw the material becoming the workpiece, then it goes up becoming the chip, right? Then at one point, right? At one point, I'll show you again. At one point, what happened? Okay, at one point, right? So metal cutting, microstructure, right? You guys see from here, right? At one point over here, the material is not moving, it's stagnated, right? Because down there is what is having positive shear, above there is having negative shear. So there has to be a what? There has to be a transition, yes or no? So where this transition occur, from negative to positive, it has to pass through what? It has to pass through this point, which is known as our 0 point, right? Zero shear stress point. So when zero shear stress occur, this is where you have what? Stagnation zone. See how useful? We are applying what again? What did we apply? Mohs circle again. Okay, not Mohs circle. Yeah, Mohs circle. Okay, right. So now we could explain stagnated zone. Okay, so now, so this is the basic mechanics that we're going to look at first. Okay, then we are going to look into the mechanics of it. Okay, we're going to look at the, I'm going to go into a very brief mechanics where we're going to write something about the material in the primary zone, okay, and the secondary zone. Let me search. Okay, so I'm going to write something out for us when the material is in the primary shear zone. Hold on. I'm not super organized today. Give me 1 minute, okay? Right. So when the material, yeah, I can get rid of this. So what I've proven to you, okay, or what I have briefly, very briefly show you is that in the primary shear zone, right? In the primary shear zone, we have